Hello everyone, welcome back to CS4540 Intelligent Agents in Learning Environments Week 3 video. For this week, we'll be taking a look at two sets of clips from two different videos from 3 Blue, 1 Brown. The first video we'll be taking a look at is back propagation step by step, and the second video that we'll be taking a look at would be brief explanation of LLMs.
A certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly,
In neural networks, the learning process revolves around minimizing a cost function. This cost function quantifies how well the neural network performs by comparing its outputs to the desired outcomes across all training examples. The cost for each example is averaged to get an overall sense of performance. To improve the network, we use the negative gradient of this cost function. This negative gradient indicates how to adjust the network's weights and biases to most effectively reduce the cost. Each component of the gradient shows how sensitive the cost function is to each weight and bias. A larger magnitude indicates that even a slight adjustment to the weight or bias will significantly impact the cost. The ultimate goal is to find the set of weights and biases that minimize the cost function. By iteratively adjusting these parameters in the direction opposite to the gradient, the network gradually learns to produce more accurate results.
on the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each
In the realm of neural networks, algorithms such as backpropagation play a crucial role in learning by adjusting the weights and biases based on training examples. A key aspect of this process is the influence of active neurons. Connections with the brightest, most active neuron in the preceding layer have the most significant impact on the network's learning, because increasing one of those weights has a stronger influence on the ultimate cost function. Additionally, the algorithm strengthens connections between neurons that exhibit high activity together. The biggest increase to weights happen between neurons which are the most active. This concept aligns with the principle that neurons that fire together wire together. Neurons that activate together for a specific input become strongly connected. Through these adjustments, neural networks refine their ability to accurately map inputs to outputs, gradually improving their overall performance and accuracy.
which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are three different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, Notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is
When training neural networks, stochastic gradient descent (SGD) is used to speed up computation. Rather than processing all training examples at once, SGD first shuffles the training data, then it divides the data into mini batches. Computing a gradient descent step for each mini batch provides a significant computational speedup compared to using the entire dataset. While each step might not be the most precise downhill direction, the overall process becomes much more efficient. By repeatedly going through all of the mini batches and making adjustments, the network can converge towards a local minimum of the cost function.
imagine you happen across a short movie script that describes a scene between a person and their AI assistant. The script has what the person asks the AI, but the AI's response has been torn off. Suppose you also have this powerful magical machine that can take any text and provide a sensible prediction of what word comes next. You could then finish the script by feeding in what you have to the machine, seeing what it would predict to start the AI's answer, and then repeating this over and over with a growing script completing the dialogue. When you interact with a chatbot, this is exactly what's happening. A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant. You add on
A large language model (LLM) functions as a complex mathematical tool that aims to forecast the next word in a sequence of text. Rather than simply guessing, it assigns a probability each potential word that could follow. Models learn to predict by processing an enormous amount of text. The amount of text used to train these models is massive. To provide some perspective, a human would need to read nonstop for over 2,600 years to match the amount of text used in training. GPT. The model's ability to predict the next word is based on parameters or weights which are refined through training. During training, an algorithm called backpropagation is used to tweak all the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all others.
weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not
Chatbots undergo an important training phase called reinforcement learning with human feedback. In this process, workers flag unhelpful and problematic predictions. These corrections provided by human reviewers further change the model's parameters. This makes the model more likely to produce predictions that users find preferable. By incorporating human feedback, chatbots can refine their responses and provide more helpful and appropriate assistance.
Not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind boggling. To illustrate, imagine that you could perform 1 billion additions and multiplications every single second. How long do you think that it would take for you to do all of the operations involved in training the largest language models? Do you think it would take a year? Maybe something like 10,000 years? The answer is actually much more than that. It's well over 100 million years. This is only part of the story, though. This whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this, chatbots undergo another type of training.
Transformers mark a turning point in language model design by abandoning sequential processing. Instead of reading text from start to finish, these models absorb the entire input in parallel. This enables more efficient and contextual understanding. At the heart of transformers are two crucial operations. The first is attention. This mechanism allows different parts of the input text to communicate and refine their meanings based on the surrounding context. For example, attention can help the model understand whether the word bank refers to a financial institution or a riverbank. The second key operation is a feed-forward neural networks. These networks give the model extra capacity to learn and store the complex patterns found in language. By processing text in parallel and using attention and feed-forward networks, transformers can generate remarkably fluent and contextually relevant text. Okay, thank you everybody for watching this week's video. I'll see you guys in the next video.